What is this doing? I mean, why isn't that making a more obvious? I mean, that looks pretty Sapinski-y. Let's see what happens if we do just a smaller grid graph. Go one more step. What? It didn't make it?
Not enough edges. It's 3 edges minimum. I see. I know what happens. So because the grid has 4, I mean, any vertex degree is 4. There are some edges on the grid that are left.
Yeah.
And that's why there's a core in there, which then messes up the whole layout.
Yes. We should probably try and start it off from a toroidal grid, if you understand what I mean.
Well, what we really need is trivalent grid, I think. So the all edges are used.
Toroidal grid, right?
Why toroidal? I mean, we could start with toroidal, but it's...
But otherwise it's going to have dangling ends.
Sure.
Which doesn't seem desirable. Because it'll just eat in from the ends, because the ends won't be able to evolve.
Well, if it's complete trivalent, the ends will evolve somehow.
Sure, but so the question is, so I looked back at the NKS book code for the trivalent graphs, and unfortunately, it's a very layout-oriented piece of code. There's no part of our
layout-oriented.
Well, I've got pictures of trivalent graphs, right?
Right.
I can,
what sort of code?
I mean, what sort of code? It's just, I'll show you. I'll show you what it is.
I mean, which code are you talking about? Evolution
I'm talking about the
or
code
plotting?
Plotting. It turns out it's more plotting than evolution.
I see. Okay.
I mean, I think I might have some evolution code, actually. Let's see here, whether this has evolution code. We can't grow our own, can we? Is there a way to grow our own grid? That would be nice to be able to do anyway.
I mean, I'm sure there is a way to do it.
Can we think
Well,
about
we just need to split hexagons. Take one hexagon and split it into multiple pieces.
Yes, but I think it's got to be, maybe it will be easier to do it with a triangular grid. Right, if we start with the tetrahedron, no, because we don't want it to Sapinski. We want it to split.
Yeah, you need to be more careful with triangles. Because we can, if we just naively insert triangles like you would expect, you know, separate 1 and 3, then the overall, I mean, the previous triangle will still be there, and it's going to mess things up.
Yeah.
With hexagons, it's kind of simpler because the outside wouldn't be a hexagon anymore.
By the way, this is a nice picture. This one that shows how, see what I'm saying? This is showing what updated on the previous step.
Yeah, I see. Well, to be fair, it's kind of hard to see, especially at the bottom.
Yes, I agree.
I think we need a dynamic one.
Yeah, I know we need a dynamic one, but we need
highlight events probably in different colors based on whether next or previous.
Yes, but we also don't. What we also want one which preserves the overall orientation of the thing.
Yeah, exactly. That's what it depends on. Well, actually, orientation is not that hard to fix probably, because we can just fit orientation.
By using what, moment of inertia or something?
No, we could just optimize, find the angle, relative angle, which is, that does keep most coordinates as close as possible.
Fair
The
enough.
problem is it's not always just orientation, because some pieces, so it might flip in some ways and so on.
Sure. Sure. By the way, those are the simplest causal invariant pure. Yeah, those are the simplest non-self-overlap graphs. I don't know what the analog here is.
It's hairs.
With hairs, yeah.
Well, we could emulate those.
No, but I don't want to do that. I mean, what we want to do is we want to find out what are the simplest, if we want causal invariance, right? One way we can do it is by having, just like with strings, we have non-overlapping strings, right?
Well,
I mean,
we cannot do it the same way here, because we can always add, in other words, if you can always just add more edges to everything, in which case you have overlaps for any input.
Let me understand that statement. Wait a minute. So there's no analog. I don't understand that. So you're saying,
Okay, suppose if we are not limited by choosing initial conditions, then let's take one initial condition which doesn't have overlaps, and then you duplicate every edge in it.
yes.
Well, now there are overlaps.
No, but what we're interested in is the rules, right? We're asking.
I know, but I'm saying there are no rules such that for any initial condition it will not have overlaps, except for trivial cases.
Why is that different in the case with the hairs and things in these graphs?
Well, because hairs limit how many edges you can have coming out of a vertex.
All right. So what are the minimal causal invariant rules? Do we know that?
Well, there have to be limits on the states. In other words, if we know that it stays trivalent and the rule doesn't change that, and if assuming the state is trivalent, it doesn't overlap, then it will be causal invariant.
I understand, but can we? Okay, so you claim there are no initial condition independent causal invariant examples. Is that what you're claiming?
Well, apart from trivial cases, yes. And by trivial cases, I mean if there is only single edge in the left-hand side or something more trivial.
Yeah. Well, that's an interesting claim. Do we have a section about causal invariance here? Let's take a look. Okay, so.
But I think it should be possible to prove causal invariance in some cases.
Right. Okay. So except for single edge rules, single edge LHS rules, causal invariance.
Well, there might be other exceptions.
Probably.
Well, there definitely are other exceptions.
Okay, so wait a minute. In what sense is this not? Wait a minute. But wait, I'm going to say causal invariance probably is contingent on
okay, we also
particular
need to
initial
distinguish
conditions.
between causal invariant and non-overlapping, because purely constructive rules are causal invariant. even though they overlap
Okay.
a lot.
Okay, non-overlappingness. I bet that's going to come up in the spell checker. Yes. Okay. So, but we need to find simplest causal invariant rules. Do we believe that Jonathan's causal invariance checker is working?
I mean, I didn't test it, but it appears to be working during the conference on a few examples we tried it on.
Okay, so then maybe what we should do is go back to our
Remember we had a circle one which had non-trivial directions.
Okay, but by the way, let's another to-do list item is to make these hexagonal grids.
Right.
Do we see how to do it just programmatically? I mean, can't we do it by looking at a hexagonal lattice?
Can you make a hexagonal lattice?
I think so.
Well, that should definitely help him. Why is it an array?
I have a bad feeling that those are its root vectors. So those are root vectors, and if what we do is we say ij times each of those, right? So we say table of I times the first thing
Yeah, I see what you're saying.
plus j times the second one and then we do a catenate on that.
Well, that will just give us points, but we need to know how points are connected.
I know. Right. It's rather boring. Okay, so how do we determine how the points are connected? The points are connected to I goes to I plus 1, j goes to j, right? I think so. We want to connect this. What do we want to do?
Well, somehow there should be 3 connections from each point.
Let me look in the NKS book. I had 2 different places where I talk about this. I talk about this in connection with, let's take a look. Really, it's convenient having all this stuff here. There we go. Okay, chapter 9. See that picture there? that has the coarsening of a planar foam.
Okay.
One way to generate connections through a completely random trivalent network with n nodes is to apply a random permutation. Gosh, that's really remarkable how much stuff was already in here. All of this, okay, anyway. Let me try to find where that source was.
Do you still have iGraph M package by any chance?
I do. What do you
That
mean?
apparently can make hexagonal grids.
iGraph? You mean it's a package that what package? Okay.
iGraph M, IG and M capital.
Okay, hold on. iGraph M. Well, I have a very old version, I think, but I could try it. That's not a good sign.
Well, did you import it?
What's that?
Did you get it?
Well, I thought I got it, but
No, I mean, it's not enough it's installed. You need to do needs of it.
I know I did that. I thought I did that with the interface though. All right, but let's try this. What the heck?
You need to retype it, right.
Okay. So what was the input that was supposed to work here?
Well, you can try one with lattice mesh.
I'm now getting excited about this. I wonder what random walks on graphs. That seems interesting. I mean, because one of the things we need to do is sort of the is I want to add subalts to my list of people. One of the things we need to do, I was saying, is figure out how we can get, we've got dimension measures, but the question is what other kinds of what other kinds of sort of global measures of graphs can we get? Like solving, like random walks on these graphs will be an example. What are the indicators of overall graph structure? Dimension just being one of them.
Well, I don't really know.
Okay, but anyway, so you're saying here, you say there's this lattice thing. You're going to send me the...
Yeah, and you can make graphs from lattice.
Okay, how does it do that?
Let's see, so the same answer has a code for it. Let me check.
Oh, he's got periodic arrow true. That's nice. It's a mess. Why isn't that looks like a hypergraph?
Okay, I have the code for doing it.
Oh, for some reason this doesn't allow me to allow pasting. Can you send it by email?
Sure. Okay.
to go in a minute. I'll be around later. Okay, let me run this. Oh, beautiful. Now what about the periodic case?
Well, that I'm not sure how to do. How did you make the other one periodic?
I said periodic
I
arrow
don't think
true.
IG mesh takes periodic.
I see. Well, but let's just take this graph and feed it into our previous thing, and then I'm going to have to go. Where was it? Random, etc. Initial conditions. Wow, it's taking its time. What's it doing? Does that have many more things that it can do? Oh God, that's a Sapinski. No. Okay, that's not what I wanted. I wanted the original, the famous splodge rule. What the heck did that do?
This is weird.
Well, maybe this thing is crazy.
Yes, it is crazy. We need to catenate it.
Does it have a very large number of updates to do, or what?
I guess. I mean, I don't know if it's graph. I don't know if it's plotting take this long. That would be strange.
I need to go. Oops, let's just try
One by
doing
one step.
Yeah. All right, let's see what happens. What is that?
Okay, something's wrong there. We didn't convert it correctly.
Well, look at this. There's a giant collection of twos there. Everything is a two.
So what? Oh, I see what happened. We still can you do index graph of this first, then do from graph?
Indexed graph?
Yeah.
Index
Index
graph.
graph. Although it should still work.
Then we don't need the catenates.
For vertex names. Yeah, we don't need the catenate.
Okay, the hedgehog has risen. Well, that's nice looking. Okay, I gotta go.
Well, if you ever want an insect, that would be the first picture here.
What? It's a lava.
If you're looking for insects, that would be the first one here. That
Yes.
definitely looks like a centipede.
Yes. Okay, I gotta go. I'll talk to you later.
Okay.
Okay, see ya. Bye.
See ya.